Hey guys, F Train here. It is actually still Monday, and I'm just recording this ahead of time so that I can take a little bit easier tomorrow on Sarah Jessica Parker's birthday. But I will be available. I'll be checking email. I'll be probably grading homework and stuff. So if you need to get in touch with me, don't worry. I'll be around. Um, but so we're going to do a lesson today is called White Dwarfs. Okay. Yesterday we talked about red giants, and basically the remnant of a red giant is eventually is a planetary nebula and a white dwarf. So do now is, why don't stars collapse under their own weight? And this is definitely something that we've talked about in the past, and especially when we talked about the pressure temperature thermostat. um, but there is that pressure pushing outward. And but then we're going to be talking about some new forces that you may not have heard about in the past today, which is also going to answer that question of why certain types of stars do not collapse. All right, so white dwarfs. Um, so if you look at this YouTube article, you will notice that the largest diamond ever was called the Cullinan diamond, and it was about 1.37 pounds, 3,106.75 carats. Okay, usually like a diamond ring, that an engagement ring is like 1 carat or something like that. Okay, so this is a lot of carats. But the largest diamond ever found is not on Earth. Okay, it is the burned out corpse of the star BPM 37093, also known as Lucy, and it's about 50 light years from Earth. Okay, and that reminded me of that song. But anyway, so let me move that up there. It's 10 billion trillion carats, so a little bigger than the average engagement ring. Question is, could this happen to the sun? So what question does this raise? And our aim for today is going to be, how could the sun turn into a diamond? So as a star leaves the main sequence, it can go through several stages. We've got the red giant stage, which we talked about in the last lesson: enormous expansion until the mass blows away in a pulsating manner. The result then is a planetary nebula, such as the Ring Nebula that we looked at. So the planetary nebula forms around it from the ejected mass. So this gas cloud, though, is surrounding a carbon and oxygen core. And that carbon oxygen core is called a white dwarf. All right, so white dwarfs are the most common type of stars out there. There's you guys are all familiar with the star Sirius. It's the brightest star, but that's Sirius A. Sirius B is 10 to the fourth times less luminous than Sirius A. It has a mass greater than the mass of the sun, 1.17 times the mass of the sun. Its temperature is 25,000 Kelvin, which gives it a color of bluish white. But its diameter, check this out, is less than the diameter of the Earth. So how would the density of a white dwarf then compare to the density of the Earth? So why don't you take a minute and see if you can figure that out. How much greater will the density excuse me, be? The density of Earth is about 5.4 0.51 grams per cubic centimeter, whereas the density of the sun is 1.41. So now you can figure it out, I think. Okay, so take a pause and see if you can determine the density of the white dwarf. All right, you're back. Density of a white dwarf is about 2 million grams per cubic centimeter. So if you were to take 1 teaspoon of a white dwarf, it would weigh 11 tons. Okay, so it's super, super dense matter. Now, why is the density of a white dwarf so high? Well, sorry, I wanted to make sure I was recording because earlier today I made a video and I forgot to hit record. I had to kind of do some of it over again. So anyway, so why is the density of a white dwarf so high? What will happen once a red giant has burned its entire helium core into carbon and oxygen but doesn't have enough mass to fuse heavier elements? Well, that to answer that question, we need to ask sort of what we did in the AIM today. How does a normal star support its weight? Well, we know that a normal star supports its weight because the core is undergoing nuclear fusion, and that tremendous amount of pressure that's being created from the nuclear reactions that are taking place is able to push out and keep the hold in the pressure from all the gas outside. Okay. Now we mentioned that as a when the core when the hydrogen core has all fused into helium, and in the case when the helium is not hot enough to fuse, it's going to contract. Okay, so how does a star support its weight if fusion is burned out? If you have a white dwarf, you're basically getting no energy from fusion. Okay, it's carbon and oxygen. The mass of the sun or a star similar to the sun is not nearly enough to fuse carbon and oxygen. Okay, so this is the final stage of that star. It's not going to be able to fuse to any larger elements. We'll learn when we learn about supernovas and things like that. We'll learn about the fact that if you have stars that are much more massive than the sun, well, those stars can actually fuse elements even all the way up to iron and even heavier. But the sun won't ever be able to do that. So you have no energy from fusion, and the star contracts to the point where it becomes what we call degenerate matter. Now, degenerate matter is basically what holds the degenerate matter, what pushes it apart, is called the electron degeneracy pressure. All right. Now, first of all, let's talk about what is degenerate matter. Okay. So if you have a low density gas, basically has only a few electrons per cubic centimeter, and you have plenty of electron energy levels available. Okay, so and so the electrons can be in different energy levels, right? But as the gas gets compressed, what happens is the electrons get raised to higher energy levels. Now, with an extremely high density gas, basically nearly all the energy levels are occupied. But what happens is they all get compressed into these energy levels here, and they're all paired up. And there's something in physics called the Pauli exclusion principle. And it states that 2 electrons cannot occupy the same quantum state. Now, what that basically means is you cannot, whereas, you can fuse a a proton and another proton together, or a deuterium and a proton together, you cannot fuse electrons together, right? They cannot. And so what happens is that the fact that they can't fuse together creates a pressure outward that prevents them from occupying the same spot. So essentially, when you're talking about a white dwarf, you're talking about the fact that you've compressed it so much that the electrons are literally like bumping into each other. And since they can't fuse together, they can't get any, they just can't get any smaller. And so the density is going to be huge. Now, degenerate matter is neither a gas or a plasma. It's very hard to compress, and this is probably one of the most important things about it. One of the most interesting things about it is that according to quantum mechanics, the pressure is not related to temperature. So in other words, as you compress degenerate matter, it does not get any hotter, okay? Nor will it expand when it gets really hot, okay? Now, since there's no fusion taking place, some astronomers don't even call white dwarfs stars. They call them compact objects. And so, as we mentioned, white dwarfs are the most common type of star. So if they're not even stars, then but a lot of people still do call them stars. All right. How would the gravity of the surface of a white dwarf compare to the gravity on Earth? You might remember the equation from physics that says that the gravity at the surface of the planet is, well, actually, we looked at this a few months ago, root gm over r, right? And so if you think about the fact that you have a huge G, all right, and you have a really, really small r, the gravity is going to be incredibly large, okay? And so, actually, I'm sorry, I messed up that equation. The gravity is gm over r squared, my bad. All right, but it's still the same idea. If you have a huge amount of gravity, huge mass, so a huge m and a very, very small r, you're going to have a tremendous gravitational field at the surface of a white dwarf. Okay. Now, why will the atmosphere of a white dwarf be so thin? Well, you can imagine if all of a sudden the Earth's gravity, got 100 times greater, it would pull the atmosphere a lot more, and it would make the atmosphere thinner. And this is what happens on white dwarfs. The gravity on a white dwarf is 100,000 times greater than the gravity on the Earth. It pulls the atmosphere into extremely thin layers. The interior, which is mostly carbon and oxygen floating in a sea of electrons, crystallizes as it cools, forms a crystal lattice, which is basically what a diamond is. Okay, and so that's why we at the outset talked about the fact that the biggest diamond is actually a white dwarf. So predict what will happen to the white dwarf once the energy of the degenerate core has cooled. So the final death of a white dwarf, all the energy is radiated into space and it becomes cold and dark. The cooling does not cause contraction, again, because it is degenerate matter. This takes billions of years and eventually becomes what we call a black dwarf. Now, this is not a black hole, okay? It's different from a black hole, but it's essentially a cooled down white dwarf. So there's probably, maybe there are a few black dwarfs out there, but we wouldn't really know about them because they're so small and they're not emitting any energy. They might even be too small to detect them with gravitational waves and things like that. Okay, so anyway, that's our lesson on white dwarfs. I'm going to link the video here that I was gonna play for you guys, and so I'll link that
along with the homework. Okay. Have a great day, and I'll talk to you guys soon.